Look up at the night sky. What do you see? You see countless stars, each one a giant ball of fire and a cosmic furnace. These stars have burned for billions of years. They are a source of immense power. From the very beginning of our time on this planet, humanity has also looked for power. Our story is a story of fire. We started with small flames in a cave. They gave us warmth. They gave us light in the darkness. They helped us cook our food. They kept predators away. This was our first great discovery. It was the first time we learned to control a piece of the universe's energy. From that first spark, our journey for energy has never stopped. We learned to harness the wind with sails to cross vast oceans. We built water wheels to grind grain and power simple machines. We discovered the immense power locked within coal. We discovered the immense power locked within oil. That discovery fueled an industrial revolution. It built the modern world we live in today. Our cities glow with electric light, homes filled with devices running on steady power, factories producing goods at unprecedented scale. Every step forward has been powered by a new way to capture energy. This long chain of discovery connects us to our past. The same drive that tamed fire now leads us to split the atom. The power grid is a much larger, more complex campfire. It is the same fundamental quest. We are always searching for more energy. We need it to be reliable. We need it to be more powerful. We need it to be abundant. Our civilization is built on this foundation. Without it, the world would grind to a halt. The lights would go out. Our progress would stop. The search for power is about survival and our evolution. But this quest has a heavy price. The fuels that built our world are now threatening it. Smoke fills the sky. The earth is warming. The climate is changing in dangerous ways. We stand at a critical crossroads. The old ways are no longer sustainable. We need a new fire, a clean fire, one that burns as brightly as the stars without burning our home. We need power that is nearly limitless, safe, clean. This is the great challenge of our time. It calls for our greatest minds and boldest dreams. The answer to this great challenge might be found back where we started, by looking at the stars. The same process that powers our sun and every other star in the universe is called nuclear fusion. It is the process of forcing tiny atoms together to release enormous amounts of energy. For decades, scientists have dreamed of building a star on Earth, a machine that could replicate the sun's fire in a controlled way. This would give us a source of clean energy that is virtually inexhaustible. The fuel for fusion comes from water, and a small amount could power a city for years. It produces no greenhouse gases and very little long-lived radioactive waste. It is the ultimate energy source. But creating a star on Earth is not the only challenge. We also need a way to store and distribute this incredible power. Our current batteries are based on chemical reactions. They are good, but they have limits. They can be slow to charge and they lose their capacity over time. What if we could store energy in a completely new way? What if we could use the strange and wonderful rules of quantum mechanics? This is the idea behind quantum batteries. These are not just better batteries. They are a fundamentally different technology. They promise to charge almost instantly and deliver powerful bursts of energy exactly when needed, revolutionizing everything from electric vehicles to stabilizing our power grids. Harnessing fusion and developing quantum batteries are two of the most complex scientific and engineering challenges humanity has ever faced. The amount of data we need to process is staggering. This is where a third pillar of our new energy age comes into play: artificial intelligence. AI is the key that could unlock both fusion and quantum storage. It can analyze vast data sets from fusion experiments in seconds. It can predict and control the chaotic behavior of plasma inside a reactor. It can help us design new materials and optimize the complex systems required for a quantum future. AI is the co-pilot on this journey. Together, these three technologies, fusion, quantum batteries, and artificial intelligence, form the foundation of a potential new era for humanity. An era of clean, abundant, and intelligent energy. An era of infinite power. But with great power comes great responsibility. How will we manage this new fire? Who will control it? How can we ensure that its benefits are shared by all of humanity, not just a select few? These are the questions we must ask ourselves as we stand on the brink of this incredible future. We are not just building new machines, we are building a new world, and it is a world we must build wisely. Table of Contents, Part 2, Act 1, Fusion Fundamentals, about 5 sections. Section 1, The Star in a Bottle. Section 2, The Promise of a Clean Fire. Section 3, The Three Great Hurdles. Section 4, The Magnetic Cage, Tokamaks. Section 5, The Twisted Path, Stellarators. At the heart of every star, including our own sun, a magnificent process is constantly unfolding. This process is called nuclear fusion. It is the universe's ultimate power source. Imagine taking the smallest, lightest atoms in existence, hydrogen, pushing them together, colliding under immense force and heat. When you squeeze them with immense force and heat them to incredible temperatures, they don't just bounce off each other. They merge. They fuse into a new, slightly heavier atom, helium. Something amazing happens. The new atom weighs just a tiny bit less than the originals combined. That missing mass isn't lost. It's converted into a tremendous burst of pure energy, E in MC2. This is the secret behind the sun's brilliant light and warmth. For billions of years, it has been fusing hydrogen in its core and powering life on Earth. Now humanity is trying to replicate this cosmic process on our planet. The goal: build a machine that acts like a miniature star, a star in a bottle. If we can control this stellar fire, we unlock an energy source unlike anything before. The fuel for this Earth-based star is easy to find. It comes from isotopes of hydrogen, heavier versions of common hydrogen, deuterium, tritium. Deuterium can be extracted from ordinary seawater. 1 gallon of seawater's deuterium yields energy of about 300 gallons of gasoline. Tritium is rarer, but can be produced inside the reactor. The reactor's walls can be lined with lithium. High-energy fusion particles strike lithium and create tritium. The reactor breeds its own fuel in a continuous cycle. This self-sustaining cycle is one of fusion's most beautiful aspects. It means a plant wouldn't need vast supply chains of rare fuels. Raw materials are plentiful and globally available. Oceans, Earth's crust. That accessibility reduces geopolitical tensions tied to fossil fuels. It promises a future where energy is a shared resource for all humanity. The most compelling reason to pursue fusion energy is its incredible potential for clean power. Unlike burning coal, oil, and natural gas, fusion does not release carbon dioxide or other greenhouse gases into the atmosphere. A world powered by fusion would be a world where our energy needs no longer contribute to climate change. We could power our cities, industries, and transportation systems without warming the planet. Beyond its climate benefits, fusion also offers a huge advantage in terms of energy density. This means that a very small amount of fuel can produce a massive amount of energy. A fusion power plant would therefore require far less land and resources than other energy sources. It would be a compact, highly efficient source of baseload energy, providing a steady and reliable stream of electricity 24 hours a day, regardless of whether the sun is shining or the wind is blowing. Another major benefit is safety. People often hear the word nuclear and think of the dangers of nuclear fission. Fission works by splitting heavy atoms, which can lead to chain reactions and the risk of a meltdown. Fusion is fundamentally different. It is not a chain reaction. It requires very specific and extreme conditions. If there is any disruption in the reactor, the fusion process simply stops. The plasma cools down in seconds, and the reaction fizzles out. There is no possibility of a runaway reaction or a meltdown, making fusion power plants inherently safe. Furthermore, the waste produced by fusion is much less problematic. The main byproduct is helium, an inert and harmless gas. This combination of zero emissions, high energy density, inherent safety, and manageable waste makes fusion the holy grail of clean energy. Section 3. The 3 Great Hurdles. While the promise of fusion is immense, the challenge of achieving it is equally enormous. To make atoms fuse together, we have to overcome the natural force that pushes them apart, Atomic nuclei are all positively charged, and like the same poles of two magnets, they repel each other very strongly. To overcome this repulsion, we need to create conditions that are truly extreme. This leads to the 3 great hurdles of fusion research: achieving extreme temperature, maintaining sufficient confinement time, reaching a high enough plasma density. These 3 factors are interconnected. The first hurdle is temperature. We are talking about temperatures over 150 million degrees Celsius. This is more than 10 times hotter than the core of the sun. It becomes a 4th state of matter called plasma. The second hurdle is confinement. No physical material can withstand direct contact. The solution is to use powerful magnetic fields, to create a magnetic bottle or a magnetic cage that traps the hot plasma. This is known as magnetic confinement. The final hurdle is achieving the right combination of confinement time and density. The energy produced by the fusion reactions is greater than the energy required to heat and contain the plasma. Achieving this energy break-even point is the ultimate goal. Section 4. The magnetic cage, tokamak. The first and most widely developed design is called a tokamak. The word tokamak is a Russian acronym that translates to toroidal chamber with magnetic coils. A tokamak is a machine shaped like a donut, or a torus. The magnetic cage in a tokamak is created by 2 main sets of coils. First, a series of large, D-shaped coils, the toroidal field coils, create a powerful magnetic field that runs the long way around the donut. To solve this, a second magnetic field is needed, which is generated by driving a massive electrical current through the plasma itself. This plasma current is induced by a central magnet, the central solenoid. This plasma current generates its own magnetic field, called the poloidal field. When you combine the toroidal field and the poloidal field, you get a twisted helical magnetic field. This helical field forces the plasma particles to spiral around inside the chamber, keeping them trapped and stable. Tokamaks have been the leading design in fusion research for decades. Major international projects like the massive ITER experiment are based on the tokamak design. However, tokamaks have a key challenge. The current in the plasma is difficult to sustain indefinitely. Many tokamaks operate in pulses. Section 5. The twisted path, stellarators. There is another, more complex design. This design is called a stellarator. It takes a fundamentally different approach. Instead of relying on a large current running through the plasma, a stellarator generates the entire magnetic cage using external twisted magnets. Those magnets wrap around the vacuum chamber. That makes the machine itself more complicated, but the plasma inside is much simpler to control. The key advantage of the stellarator is its potential for true steady-state operation. The plasma inside a stellarator is also inherently more stable. However, this stability comes at the cost of immense engineering complexity. It's only with powerful supercomputers for simulation and advanced manufacturing that modern stellarators became a reality. Now, a friendly competition exists between the two concepts. Both tokamaks and stellarators are pushing the boundaries of science and engineering, and both are essential in our global quest to build a star on Earth. Section 4. The Ghost in the Machine. AI enters the reactor. The quest for fusion is not just a story of magnets and plasma. It is also a story of data. For decades, scientists have had to sift through this mountain of data manually. A slow, painstaking process. This process could take months or even years for a single experiment. This is where a new, powerful ally has entered the scene. Artificial intelligence. AI, and specifically machine learning, is changing the game for fusion research. They can analyze the torrent of data from a fusion reactor in real time. They can see patterns that are invisible to the human eye. They can learn the complex, non-linear relationships between the thousands of variables. One of the most exciting applications is in predicting and preventing plasma disruptions. The AI learns to recognize the subtle warning signs that precede a disruption, often tens or even hundreds of milliseconds before it happens. This is enough time for the control system to take action. It can inject a small amount of gas to cool the plasma safely. It can adjust the magnetic fields to steer it away from instability. Beyond just analyzing data, artificial intelligence is now taking an active role in controlling the plasma. This concept of a digital twin is central to AI's role in fusion. The AI was given control over the reactor's magnetic coils. It quickly learned to manipulate the magnetic fields with a level of precision and creativity that surprised its human creators. It discovered new and more efficient ways to sculpt the plasma. AI is also being used to accelerate the design of new fusion reactors. It is becoming an indispensable tool at every stage of the process, dramatically shortening the path toward a future of clean, limitless fusion power. Table of Contents, Part 4, Act 3, Quantum Batteries and QUILLIUM'S Explanation, about 5 Section. Section 1, The Limits of Our Chemical Cages. Section 2, A New Idea, The Quantum Leap in Storage. Section 3, QUILLIUM'S Corner, Superposition and Collective Power. Section 4, QUILLIUM'S Corner, The Entanglement Advantage. Section 5, From Theory to Reality, The Quantum Grid. Section 1, The Limits of Our Chemical Cages. Humanity's mastery of energy isn't just about generation, it's also about storage. Our modern world runs on batteries. They work by shuffling ions, tiny charged particles, from one material to another. But this chemical process has fundamental limits. Charging a conventional battery is a slow, sequential process. Furthermore, every time you charge and discharge the battery, a little bit of damage is done. Its capacity fades. Another key limitation is power density. How fast you can release that energy. Chemical batteries struggle to respond that quickly and at that scale. They are like a large, slow-moving river, not a powerful, crashing wave. We need a new kind of storage that is not just a bigger bucket, but a fundamentally different way of holding and releasing energy. To find this solution, scientists are turning away from classical chemistry and looking toward the strange and wonderful world of quantum mechanics. Section 2. A New Idea, The Quantum Leap in Storage. What if we could store energy not in chemical bonds, but in the very fabric of quantum reality? This is the radical idea behind the quantum battery. The true magic of a quantum battery lies in how it charges. A quantum battery could leverage a principle called collective charging. It might be possible to charge all the tiny quantum switches at the same time. A quantum battery with 1 million atoms could theoretically charge 1 million times faster than a single atom. This incredible charging speed could change everything. Imagine an electric car that could be fully charged in the time it takes to fill a tank with gasoline. To understand how this is even possible, we need to dive into the quantum realm itself. And for that, we turn to our AI co-host, QUILLIUM.
Section 3, QUILLIUM'S Corner, Superposition and Collective Power. Hello, I am QUILLIUM. To understand a quantum battery, we must first think differently about how things can exist. In your everyday world, a light switch is either on or off. But in the quantum realm, things are more flexible. An atom can be in a low-energy state, on, or it can be in superposition, both at once. Think of it like a spinning coin before it lands. Imagine a jar filled with 1 billion of these spinning coins. A classical battery would be like going to each coin, one by one. That takes a very long time. A quantum battery can take advantage of the collective nature of these qubits. Instead of sending a tiny packet of energy to each qubit individually, we can send a carefully prepared pulse of light. Because qubits are in superposition, they can all absorb energy from this field simultaneously. This idea also applies to discharging. If they all push at exactly the same moment, in perfect synchrony, they can generate a huge amount of force. A quantum battery can make its qubits work together in this way, releasing their energy in a powerful, coherent burst. Section 4. QUILLIUM'S corner. The entanglement advantage. There is another quantum trick that can make these batteries even more powerful. It is called quantum entanglement. When 2 or more quantum particles become entangled, their fates are linked. They behave as a single entity, even if they are on opposite sides of the galaxy. This profound connection can be harnessed. By entangling them, we create a highly correlated system. The qubits act in perfect unison like a perfectly drilled marching band. Entanglement can also help protect the stored energy. One of the biggest challenges is decoherence. Entanglement can create protected states more resilient to noise, allowing the battery to hold charge longer. So, combine superposition, collective charging, and entanglement. A recipe for revolutionary energy storage. We are learning to command matter and energy at the most basic level.
Section 5. From theory to reality. The quantum grid. For quantum batteries, the hurdles are significant. We must control and entangle not just 2 or 10 qubits, but millions or billions of them. Early applications may be hybrid systems. Imagine a power grid driven by a massive fusion reactor, a huge, steady supply of clean energy, stored in large, conventional battery farms for long-term needs, and a small quantum battery for instant, high-power response. It could stabilize grid frequency after a sudden surge, discharging immense power in a microsecond, acting as a shock absorber. Fusion energy and quantum storage, perfect partners. Fusion, a near-infinite source. Quantum batteries and other storage give control and flexibility. A grid that is clean, abundant, resilient, and responsive. Section 1. A new fire, a new world. We began our journey with a look at the stars. We have now come full circle. We stand on the verge of bringing the fire of the stars down to Earth. This is the promise of fusion energy. But to build this world, we need more than a powerful generator. Enter the other 2 pillars, quantum batteries, and the 3rd pillar, artificial intelligence. Together, fusion, quantum batteries, and AI form a trinity that can reshape our relationship with energy and our world. This convergence is more than a tech upgrade. It could be a turning point for our species. Scarcity could become abundance. Conflict over resources could fade into history. Environmental damage from old fires could begin to heal. Section 2. The awesome responsibility. With the prospect of near-infinite power comes an awesome responsibility. This new fire can be used to build or to burn. The same AI that can optimize our energy grids could be used for surveillance and control. As we develop these powerful tools, we must simultaneously develop the wisdom to wield them correctly. One of the most pressing questions is that of equity and access. Who will own these new technologies? If this immense power becomes concentrated in the hands of a few nations or a few corporations, it could create new global inequalities. We must work to ensure that this is a technology for all of humanity. This requires open-source research, international collaboration, and policies that promote the fair distribution of this new energy wealth. Finally, we must remain humble stewards of our planet. The goal is not just to replace one energy source with another, but to build a system that works in harmony with our planet's ecosystems. Infinite power demands that we become more mindful and more responsible than ever before. Section 3. The dawn of the stellar age. Look up at the sky one last time. For all of human history, we've looked at the stars with wonder. We are entering an age where we won't just look at the stars, we will build them. Imagine a future city, no smoke, no carbon, no pollution. The road ahead is long, yet every great leap once seemed impossible. We rise to the challenge. We push the boundaries of what's possible. Our quest for fire has brought us to this moment. We stand at the threshold of a new era. The choice is ours: scarcity and conflict, or working together to build wisely, to light a fire that will warm all of humanity. The future of energy is the future of civilization, and its dawn is upon us. You're watching Apexitech, decoding the tech that's building tomorrow.